You're a Swiftie, and you just streamed Anti-Hero 53 times. Suddenly, Spotify automatically plays Olivia Rodrigo, another artist you also love. But how did it know what to play next? This is not magic. It's math disguised as a random shuffle button. But how does it actually work? Spotify is part detective and part chef. First, it investigates what you and millions of other Swifties are listening to. This is done using a technique called collaborative filtering. And then it also analyzes the content of the song characteristics. All of this mixed together, and boom, Olivia Rodrigo ends up on your Discovery Weekly. This is known as a recommendation system. It's the same that online shops use to suggest products, streaming services to show their movies, or social media platform to show you content. Remember, we have mentioned two core concepts. Content-based reasoning captures the individual user preference, mainly using historical data. On the other hand, collaborative filtering collects knowledge of the community. It is based on the simple assumption that if two users are similar, they are likely to enjoy the same things. Now, let's analyze how Spotify uses this, changing a little bit the example. You're having a moment listening to Coldplay, when suddenly Believer by Imagine Dragons plays next. You didn't pick it, it's not on a playlist you made, but somehow it fits the mood perfectly. What's going on? Well, Spotify likely used some method to line the app just right. Starting with content based reasoning, Spotify analyzes the musical features of the music you listen to. For example, it takes into account the tempo, key, genre, and even uses natural language processing on lyrics. Spotify connects the dots. These two feel the same. The cool part, it doesn't need to know you. It just needs the song. So it works even when you're a brand new user. The downside, it can get stuck on feedback loops. Like you listen to one Ed Sheeran song and suddenly enjoy 10 years of wedding music. Now let's talk about collaborative filtering, Spotify's other trick. Instead of analyzing songs, it analyzes people. It checks what other Coldplay fans are listening to and thinks, 10,000 of them also vibe with Imagine Dragons? Let's roll with it. This allows to catch weird human trends, like why do metalheads love Taylor Swift? No idea, but here you go. It also has the ability to surprise you easily. You'd never search for Norwegian folklore, but here's a playlist because 5,000 similar users did. However, it deals with several issues like the cold start problem. This is when the user is new and hasn't listened to many songs yet. It tends to create an overcrowding bias. Like, oh, you like one indie song? Well, time for 40 weeks of Billie Eilish. And finally, it's also susceptible to peer pressure. Since everyone else is listening to espresso, now you will like it too. So, what's the truth? Spotify doesn't pick sides. It uses both methods. Because why not? Content based nails the sound, and collaborative filtering nails the vibe. Okay, all this sounds great in theory, but how does Spotify actually do it? Like we said at the start, under the playlist and predictions, it's just math, stats, and a whole lot of data. Now it's time to peek under the hood. Let's break down how Spotify recommendations engine really works. We'll start with the content based side. This part is all about finding songs similar to what you already like. The first step, collecting data. Spotify doesn't ask. You tell it everything just by listening. What songs you play, how long you listen, what you skip, what you save, and what you add to your playlists. That's called implicit feedback because it's based on what you do, not what you say. All that listening data, it ends up in something called a user item matrix. Each row is a user, and each column is a song. And each cell shows how much a user interacted with the song. Played it on repeat? Maybe that's a 5. Or skipped it in 3 seconds? That's a 0. Pretty cool, right? But here's the thing. Most of that matrix is empty. No one's listened to every song, and Spotify has millions. But those blanks, they're not a problem. They're an opportunity. We can predict them. That's where the math kicks in. In a recommendation system, the user item matrix can be huge, thousands of millions of users and items. To deal with this massive, mostly empty matrix, Spotify uses matrix factorization. Think of it like this. Instead of working with one giant, messy matrix, we break it into two smaller ones, one for users and one for songs. These contain latent vectors. They are like personality profiles, but just for music. A user's vector captures each person's musical taste, and a song's vector captures the hidden features of each track. Here's the best part. Once we've created these smaller, complete matrices, we can rebuild the big one. That means we can predict how much you'd like a song you've never heard, just by checking how your taste vector lines up with the song's vector. And that's how matrix factorization powers recommendations, by uncovering hidden patterns in your listening habits and filling in the blanks with smart guesses. Alright, let's walk through a real-ish example of how matrix factorization actually plays out. Imagine we've got 3 users and 6 songs. 5 of the songs are in Spanish, 1 is in English. We already start to see 2 hidden themes, reggaeton energy and English pop vibes. As a quick overview, we can see that user 2 really likes reggaeton but not pop. User 3, totally the opposite. And user 1, we know they like reggaeton, but we don't know about the pop. For the rest, here's where matrix factorization kicks in. At first, our new matrices will be filled with random numbers, just wild guesses. To keep things simple, let's say we only use 2 latent factors. In real life, Spotify might use 10, 50, or even more than 100, but 2 is enough for this demo. These 2 factors, they'll end up capturing something like reggaeton energy and pop vibes. Important note, the algorithm doesn't know these meanings. It just detects hidden patterns based on the data. So, while we as humans can look back and say, hey, this factor probably means likes reggaeton, the algorithm never labels them that way. Now, as we saw, by multiplying our 2 smaller matrices, we can reconstruct a full ratings matrix, now with no missing values. We could say, great, let's just plug in those guesses to replace the missing ratings. But hold up, it's not that easy. Remember we started with random numbers, so the first reconstruction, it's close-ish, but not quite right. Some of the new ratings match what we expected, others not so much. The algorithm will have to tweak the numbers in both matrices. For that, we need to start with something we do know. Say user 1 rated a song with a 4. Using our current user and song vectors, the model predicts an approximate rating for this. The error is the actual rating minus the predicted rating, totaling 0.25. To fix this small error, we'll use a technique called alternating least squares, or LAS for short. LAS iteratively tweaks the user and item vectors to minimize the error. To understand it visually, imagine this is the composition of a user and item that corresponds to a rating of 4. Right now, after random initialization, they are a bit too far apart. So the predicted rating is off. LAS nudges them closer together, so the reconstructed rating moves closer to the true rating, in this case 4. To do this, LAS uses a simple formula that adjusts the values in the right direction. At each step, it alternates. First, it adjusts the user to get closer to the item, then it flips, adjusting the item towards the user. This back and forth happens gradually, with a small step size called the learning rate. Let's choose 0.05 since our error is not too high. For each latent feature in our vectors, LAS applies the rule to update its value slightly, inching it closer to the ideal. We repeat this for all known values and keep updating their vectors. And guess what? After just one step, we recalculate the predicted rating for the song, and it jumps from 375 to 399, almost spot on with the real rating of 4. The system will keep repeating this process, refining the vectors until all of the predictions get really accurate. When we finish, we can choose any song with a high predicted rating and recommend that one. But wait, where are the actual song features like BPM, genre, key that we mentioned at the beginning? Well, here's the thing, the latent factors do represent the contents of the song, but implicitly. We don't explicitly label them as tempo or genre. The algorithm just figures out which hidden patterns best explain the preferences. Think about it. Even if you don't know the technical details, part of why you love certain songs is that they share some kind of pattern, a vibe, or a mood. When we reconstruct the matrix, each latent factor combines these subtle patterns to help recommend songs. Now, you might wonder why go through all of this if you could just compare songs directly by their musical features? Well, here's why. Two songs might have the same BPM, key, or genre, but still feel totally different. Directly matching features ignores hidden complex factors like mood, cultural context, or production style that shape how we perceive similarity. For example, one latent factor might capture nostalgic summer vibes, while another groups songs by emotional intensity. And that's the magic of matrix factorization. It uncovers hidden patterns behind what we like, making recommendations that feel personal and intuitive. Now, just predicting ratings isn't enough. If you love reggaeton, you will end up with high predicted scores for all reggaeton songs. But which ones should Spotify actually recommend? Sure, it could just randomly pick some, but that wouldn't make for very smart recommendations. We need a way to prioritize the best songs for each user. Spotify found that integrating collaborative filtering, they can make recommendations smarter, while also narrowing down the huge search space. Remember, collaborative filtering is about looking at what people similar to you are listening to. The key? Give more weight to songs that people like you enjoy. So, we need to know who is similar to you. But here's the catch, how do we find them? We could, for example, check what the people you follow are listening to and recommend that. Well, not really. Let's be honest, Spotify isn't exactly a social network. You might follow some artists, some podcast creators, or even a friend or two. But as Spotify started to notice, the truth is that users don't tend to interact with or follow each other. So, how does Spotify still manage to find users like you without needing a friends list? Easy. They looked at the user's matrix. Each user in the matrix is represented by a vector, a kind of fingerprint that implicitly captures their listening habits, music taste, maybe even demographics. If we visualize these user vectors in a simplified and reduced space, distinct groups start to form naturally. To identify these groups, Spotify can use k-means clustering, a technique that you are probably already familiar with. If not, check out my video that breaks that down. K-means basically takes all those user vectors and groups them into k clusters. In this example, let's say 4 clusters. Why do this? Because we infer that users in the same cluster behave similarly. Once all of the clusters are set up, when it's time to recommend songs, Spotify will look for users most similar to you within your cluster. This is where the idea of nearest neighbors comes in, and an algorithm called k-nearest neighbors helps find them. It uses distance measures to calculate how close you are to each other. So first, it finds your nearest neighbors. Then, it boosts songs those neighbors love. If, say, 15 out of 20 of your closest neighbors are obsessed with a certain song, that track will get pushed higher up in your recommendations. By doing this, Spotify narrows down the huge music catalog, focusing only on what people like you enjoy. If we started with millions of songs, clustering in KNN might cut that down to a much smaller, more relevant set. For example, we can cut the recommendations on 4.8. And that's how platforms like Spotify use math to almost read your mind. From matrix factorization to clustering users into hidden taste groups, these clever tools power the playlists and suggestions that feel like they just get you. Want to test how well you really understood this? I've put together a quick, fun quiz, link below. No pressure, just a way to challenge yourself. Thanks so much for watching, and I'll catch you in the next video. Happy listening!